in the next few lectures we would look into the other segments of an optical communication link, that is optical sources on the transmitter side and optical detectors on the receiver side. So, if you have this optical communication link, then you have electric signal which modulates the light source. This electric signal contains the data. So, it has got electric pulse train. This electric pulse train modulates light source and generates optical pulses. These optical pulses are sent through this transmission medium, which is optical fiber, and these optical pulses, after travelling through this optical fiber, now are received at optical detector and are converted back into electric signal. So, in the next few lectures we are going to look into light sources for optical communication and optical detectors. Let us look at light sources. What are the requirements? Optical communication is primarily done at two wavelengths, 1300 nanometer wavelength, which is 0 dispersion wavelength, and 1550 nanometer wavelength, which is minimum attenuation wavelength. So, our sources should be able to give me wavelengths this or this. Then I should have line width as small as possible. Typically the line width should be smaller than or of the order of 1 nanometer. Third thing is, since I am going to use these sources for optical communication, so I need to modulate them. I need to generate optical pulses from electric pulses. So, these sources should be able to get modulated at speeds in excess of several Gbps, and also with all these qualities the sources should be efficient, they should be compact. I would not like to use a source which is this big. I would like to have a source as small as possible. They should be reliable. There should not be any malfunction during the process while sending the signal. They should be durable. I need not to replace them time to time. And on top of all these, they should be less expensive, because we want to have more and more data. We want to transmit more and more data, but we do not want to pay for it. Okay? We do not want to pay more for it. So, they should be inexpensive, they should not add to the cost. How do we make these sources? These sources are primarily based on semiconductor optical materials. Semiconductor materials, and two primary sources are light emitting diode LED and laser diode LD. So, to understand these two sources, we will discuss about these two sources in these lectures. So, to understand the working of these and characteristics of these sources, first let us look at semiconductors. Let us briefly discuss the basics of semiconductors which we are going to use in these sources. We know that the semiconductors are the materials whose conductivity lies between the conductivity of the insulators and the metals. Conductivity of semiconductors can be enhanced by order of magnitude by doping and or by temperature variation. In semiconductors we have bands. How a semiconductor conducts electricity, how its conductivity changes with temperature, how its conductivity varies with doping. To understand that, we will have to look into the energy bands of a semiconductor. What are energy bands or energy levels? If we look at a single atom, single isolated atom, then its potential energy is something like this. The electron in an atom experiences the potential something like this, the potential energy something like this. And quantum mechanics tells me that if an electron is subjected to this kind of potential energy, then it has certain bound states, it has discrete energy levels. It can occupy this energy or this energy or this energy and no energy in between. We know this from quantum mechanics. But if I have a molecule, that is, I bring another atom closer to this, then the electron now is shared by both the atoms and it experiences a net potential energy something like this. As a consequence, this energy level gets split into two and this also. So, these energy levels get split. If I bring more and more atoms, then there would be more and more splitting and these energy levels are then transformed into bands. These are known as energy bands. The highest fill band is the valence band and the immediately next to that is known as conduction band. So, what I have a valence band and a conduction band. In between I have a gap, okay, that is in between there is energy which electron cannot occupy. So, this is known as band gap and is denoted by Eg. If I have an electron in this kind of solid, then how its energy varies with k. K is the wave vector. I know that if an electron is moving, then a moving electron has a momentum associated with it and a moving electron also has a wave associated with it. Okay. If the wavelength of the wave associated with electron is lambda, then k, which is the wave vector, it is given by 2 pi over lambda and this the momentum associated with this electron is h over lambda, or I can write it down as h over 2 pi times 2 pi over lambda. This is from de Broglie hypothesis. H over 2 pi I represent by a symbol called h cross, then this p is equal to h cross k. Now, if electron is in free space, then its kinetic energy can be given by E is equal to p square over 2 m. Or I can write down it, I write it down as E is equal to h cross square k square over 2 m. In free space, any value of energy is possible, because electron is not bound to have certain discrete energies, but it can occupy any energy. It is in free space or it is in constant potential. Then the relationship between the E energy of the electron and k, which is the wave vector associated with the wave of the electron, de Broglie wave of the electron, is given by E is equal to h cross square k square over 2m. So, if I plot it, then it goes like this, it is parabolic. So, electron can occupy any energy. However, if the electron is subjected to this kind of potential energy, then what happens that it can occupy energies here, it can occupy energies here, but it cannot occupy energies here. Then this EK diagram changes. So, you have energies here in the valence band and the energies here in the conduction band, and in between there is a break. You cannot have any, the electron cannot have any energy. So, this is the band gap. Then the EK relation is modified as near the top of the valence band, the energy is given by EV minus h cross square k square over 2 mv, where mv is the effective mass of the electron in the valence band, and near the bottom of the conduction band in an SC, SC stands for semiconductor, E is equal to EC plus h cross square k square over 2 mc, where mc is the effective mass of the electron in the conduction band. These EK relations become very important and become very handy while understanding the properties of a semiconductor. Now, depending upon how the EK diagrams of a semiconductor look like, I can have indirect band gap semiconductor and direct band gap semiconductor. If the top of valence band and bottom of conduction band, they have different k vectors, different values of k, that is, this one is not on top of this in line, then this kind of semiconductor is known as indirect band gap semiconductor. Silicon is an example of this. Silicon has a band gap of about 1.1 electron volt and its conduction band is displaced along k axis with respect to the valence band. So, for a transition between these two, that is valence band and conduction band, transition between the top of valence band and bottom of conduction band would now require change in the value of k, that is the change in the momentum of the electron. So, this kind of materials, since they involve the change in momentum, and this is also known as phonon transition, then these cannot be used as efficient light emitters. However, the semiconductor materials whose top of valence band and bottom of conduction band have the same value of k, then the transition between them is direct. This transition does not involve any change in momentum or involvement of phonon. Then these kind of materials are known as direct band gap semiconductors. An example of this is gallium arsenide, whose band gap is 1.42 electron volt, and these kind of materials can be used as efficient light emitters. So, if I look at a semiconductor at 0 Kelvin, then what I find that the valence band is completely filled and conduction band is completely empty, and therefore, since conduction band is completely empty, So, there are no electrons available for conduction and the semiconductor is a perfect insulator at 0 Kelvin. The band gap of a semiconductor typically lies between 0.1 electron volt and 3 electron volts. For silicon it is 1.1 and for gallium arsenide it is 1.42. However, if I raise the temperature of a semiconductor, then some of the electrons from valence band get thermally excited to the conduction band. So, now you have some electrons available in the conduction band and some vacancies are created in the valence band. So, these electrons now can move in the conduction band if you apply electric field, and these vacancies can be filled by the nearby electrons. So, the electron can move from here, so it will create a vacancy here, then from here to here, then it will create a vacancy here. So, movement of electron in this direction is equivalent to movement of vacancy in the opposite direction, and since the electron is leaving a vacancy, so in the vacancy I can say it has got equivalent positive charge and this is known as hole. Okay. So, I have free electrons now available in the conduction band and holes are available in the valence band which contribute towards conduction. So, I can enhance the conductivity of a semiconductor if I raise the temperature. Another way of increasing the conductivity is by doping. Okay, I will talk about that later. So, if I look at free carriers in an intrinsic semiconductor which is not doped, then at T is equal to 0 Kelvin, I do not have any free carriers in the valence band or in the conduction band. However, at elevated temperatures I have some holes available in the valence band and some electrons available in the conduction band. These blue circles represent here electrons and red circles here represent holes. I can also increase the conductivity of the semiconductors by doping, and I can dope the semiconductor either by pentavalent atoms or by trivalent atoms. If I do doping of pentavalent atoms, then 4 out of 5 valence electrons of this pentavalent atom make bond with the semiconductor materials, 4 valence electrons of semiconductor material, and 1 electron is now available, it is left. So, which is now available for conduction. So, equivalently what I have a positive ion core because this electron is not associated with the atom now. So, atom has given out this electron. So, effectively I have this positive ion core and large number of these electrons available depending upon the doping level, okay, for conduction. And this kind of material is known as p type semiconductor. I am sorry, this type of semiconductor is then known as n type semiconductor because now you have negative charge electron available for conduction. If you dope it with trivalent atoms, then 3 valence electrons of these atoms make bond with 3 electrons of the semiconductor and 1 vacancy is left, okay. 4th one does not get bonded, so a vacancy is left. So, this vacancy is hole, a missing electron which is equivalent to a positive charge. So, this can be thought of as some negative ion core with some positive charges whose charge is exactly the same as that of electron. So, you have positive charges holes available here for conduction in the negative ion core. So, this kind of semiconductor material is known as p type semiconductor. So, apart from these silicon, germanium, these kind of semiconductors which have just one element from fourth group, I can make semiconductor by mixing the elements from fifth group and third group. So, what I can do? I can take the elements from third group of periodic table like aluminum, gallium and indium, and I can take from fifth group of the periodic table like phosphorus, arsenic and antimony. I can take one from here and one from here and make a semiconductor which is known as binary semiconductor. Gallium arsenide is one example of this. Aluminum phosphide is another example. Gallium antimonide is another example. Indium phosphide yet another example. Then these are binary semiconductors. I can also have two elements from third group in different proportion and one from fifth group. So, if x fraction of aluminum is combined with 1 minus x fraction of gallium from third group and then with arsenic of fifth group, then I can make aluminum gallium arsenide. This is a ternary semiconductor. You can also have 2 from third group and 2 from fifth group. So, x fraction of this 1 minus x fraction of this from third group and y fraction of this from fifth group and 1 minus y fraction of this from fifth group. Then I can make what is known as quaternary semiconductors. What is the advantage of doing this? The advantage of doing this is that I can tune the band gap. When I change the composition, then the band gap of the material changes. So, I can tune the band gap. So, here what has been plotted is the composition of various semiconductors, okay, whether it is quaternary, ternary or binary, their band gap energy and band gap wavelength, corresponding band gap wavelength. I would like to mention here that in this lecture and in the subsequent few lectures, I have adopted several illustrations from the book Saleh and Teich, which is the textbook I have recommended, Fundamentals of Photonics. So, you can refer to that book also. So, if I now find out the band gap wavelength corresponding to this band gap energy, so it is given by Hc over Eg, then it is convenient to write it in this particular form. Okay. How? Well, H is equal to 6.6 into 10 to the power minus 34, which is Planck's constant. It is in joules second. So, I can convert it into electron volt second if I divide it by 1.6 into 10 to the power minus 19, which is the charge of an electron. Then C is 3 into 10 to the power 8 meters per second. Then I can have this as 1.24 divided by Eg. This will give you 1.24 into 10 to the power minus 6. So, 10 to the power minus 6 will give you wavelength in micrometer, and then this EV basically reflects here, that is Eg will have to now input in EV. So, you can immediately find out the band gap wavelength if you divide 1.24 by Eg, where Eg is in electron volts, and then the wavelength you will get in micrometer. So, you can see that you can have a variety of Eg and correspondingly different band gap wavelengths. These are some important semiconductors, their band gap energies and band gap wavelengths. So, and also the type of the semiconductor. So, you can see germanium has a band gap energy of about 6.6 electron volt, which corresponds to band gap wavelength of 1.88 micrometer, and it is indirect semiconductor. Well, silicon has a band gap energy of 1.1 electron volt, corresponding band gap wavelength 1.15, it is also indirect semiconductor. You can look at gallium arsenide, which has band gap energy of 1.42 electron volt, band gap wavelength of 0.87 micrometer, it is direct band gap semiconductor. Indium phosphide 1.35 electron volt band gap energy, 0.92 micrometer band gap wavelength, it is direct band gap semiconductor. By changing the composition of the material, I can have whatever wavelength I want in a particular range. For example, I can find the composition of indium gallium arsenide phosphide for making light sources at 1.3 micrometer, this should be micrometer and this also micrometer. So, at 1.3 micrometer and 1.55 micrometer wavelengths. So, I can find the composition of indium gallium arsenide phosphide for making light sources at 1.3 micrometer and 1.55 micrometer wavelengths. I know, and it is given that for lattice matching of indium gallium arsenide phosphide with indium phosphide, x should be equal to 0.45 y, and the band gap energy of this material is given by 1.35 minus 0.72 y plus 0.12 y square in electron volts. So, how to get the composition? So, since Eg is given by this, and I know that lambda g is equal to 1.24 divided by Eg. So, if I want to make a source at 1.3 micrometer wavelength, so I can find out Eg corresponding to 1.3 micrometer here. So, this gives me Eg is equal to 0.954 electron volt. If I put it back into this equation, this is a quadratic equation, I can solve it and get the values of y. This will give you of course two values of y, and you will have to discard the value which is larger than 1, because y is a fraction, it cannot be greater than 1. The other value comes out to be 0.611, and it gives you x is equal to 0.275, because x is equal to 0.45 y. So, I can have the complete composition of indium gallium arsenide phosphide for lambda g is equal to 1.3 micrometer. I can do the same for 1.55 micrometer. So, for 1.55 micrometer Eg will come out to be 0.8 electron volts, and this will give you the composition of indium gallium arsenide phosphide like this. So, now what is the probability of occupation of an energy state? Okay. At absolute 0 temperature, all the electrons will occupy the lowest possible energy state, because they are not agitated, thermally agitated. So, the valence band would be completely filled and the conduction band is completely empty. If you elevate the temperature, then some electrons from valence band are thermally excited to the conduction band, and some states in a conduction bands are occupied. Correspondingly, you have some empty states in the valence band. Then the probability of occupation of energy state E is given by a function which is known as Fermi function, and is given by F e is equal to 1 over 1 plus exponential E minus E f over k B t. This kind of statistical distribution helps us to understand the properties of a semiconductor and electrical and optical characteristics of a semiconductor. So, we will look into the characteristics of semiconductor and how we can make LED out of these semiconductors in the next lecture. Thank you.